how do you picture this large number of degrees of freedom at the end of the world brane?
I mean, we just we get to choose the content of our theory, right? Like you know, like this. Yeah, we're just constructing this 1 + 1 dimensional theory, and we take it to have a large number of degrees of freedom. Now, you might worry that that would create problems or inconsistencies, but at least for the calculations that we'll do, then it doesn't. And you could say, okay, it's not physical, like in you know, higher dimensions constructions or whatever, then maybe that's not a well-defined non-perturbative thing, even though it is in 1 + 1 dimensions. But all we're using it for is to just find the simplest way we can to sort of construct a state that has this large amount of entanglement between interior and exterior. And there's no obstruction to creating a large amount of entanglement between interior and exterior in higher dimensions. That just naturally happens when you let a black hole evaporate. So yeah, I think worrying about like whether you can come up with, say, a string theory construction that gives you this ridiculously large number of degrees of freedom on the end of the world brane is sort of not the point, right? This is just really a toy example that where you can like do the calculations explicitly. And then, as I'll show in the second part of our talk, the like basic conclusions, you know, even though you can't do the full path integral anymore, go through exactly the same in sort of realistic theories of gravity. High dimension.
Just one question, or a comment actually. So we know that JT gravity, at least at low energies, is dual to the SYK model. And the SYK model has microstates actually, which were discussed by Kurkula and Maldacena. So what is these states I that you have? Are they somehow related?
I think they're certainly loosely analogous to those states. I think if you start, you know, just as if you really like want to think about JT gravity as like a fully defined non-perturbative theory, then it, you know, beyond the sort of Schwarzian sector, then it's just not the same thing as SYK, even though it looks sort of similar. These things aren't quite the same thing as Kurkula and Maldacena states, but they're morally pretty similar. And in fact, you could do, you know, you can numerically find saddle points that correspond to the saddle points I'm going to be talking about in the SYK model. We only did that for sort of two-sided states in the SYK model, but I'm pretty sure you could do it for Kurkula and Maldacena states, and it would go through the same way. And you know, those states would genuinely be analogous to the states we'll have with the end of the world branes. But it's not a perfect duality as with anything with SYK and JT. Cool. Okay. So yeah, the basic point is going to be that when we take these number of these states, which I'm going to call K, to be bigger than e to the Bekenstein-Hawking entropy, then naively it seems like the entanglement between Hawking radiation and interior is given by log K, and that is bigger than the Bekenstein-Hawking entropy. So we seemingly have an information paradox. Okay. But we want to, you know, let's try and actually check that. The great thing about this model is we can just calculate everything explicitly. So we want to just do the path integral and calculate the von Neumann. So that's sort of easily said, but it's a slightly non-trivial thing to do. So how do you calculate von Neumann entropys using the path integral? Well, the answer is that initially you want to forget about the von Neumann entropy. It's too hard. And instead consider something called an integer n Raney entropy, which is given by this formula for integer n strictly greater than 1. And as you can see, this formula is really determined by trace of rho to the n. Trace of rho to the n is just the expectation value of an operator on n copies of the system. It's just expectation of the operator that permutes those different copies around in the cycle. So this is something we're going to be able to evaluate with a path. This is something called the replica trick. And then all we're going to do is we're just going to find a formula that's sort of a function of n. This is not quite what we're going to do, but it's morally analogous to it. And then we're just going to take that function note that this thing is analytic and analytically continue to n equals 1. And if you take the limit of this formula when n equals 1, then it's easy to see by L'Hopital's rule that you in fact get the bond minus trace of rho log rho. Okay, so that is the strategy and the sort of key idea, the thing that's going to give us the unitary page curve answer rather than the Hawking information loss answer is that when we do the gravitational path integrals on n copies of the system, we're going to include topologies that connect together these different replicas via space-time worm. Okay? And that's going to magically make everything work out. So let's just start by doing this. We're going to start by calculating the sort of simplest case, which is just trace of rho squared, something called the purity. Like a decent measure of the von Neumann entropy. Determines the so-called Rayleigh 2 entropy. Okay, so we want to evaluate this thing. Just given based on the formula I showed for the previous slide for how we're constructing our entangled states, then it ends up just being given by this formula. Sum over modulus squared its inner products with the states, the black hole microstates are just getting summed over just because we had this orthonormal basis of states for reference. So this formula is just a prescription for a Euclidean path integral. What is that prescription? It says that you should, do quantum gravity, so you should sum over all topologies, integrate over all geometries with certain boundary conditions. And in this case, these boundary conditions, we have two copies of psi I, psi j. Okay, psi I, psi j, just you have an end of the world brane inserted here in state I, then you have a Euclidean boundary for a while, and then you have an end of the world brane inserted in state j. And we have two copies, one complex conjugated, so we have these two boundaries with sort of time going opposite direction. Okay, Euclidean time going opposite direction. So now we have to look at the sort of topologies that have these boundary conditions. And there's a lot of them, but the only two that will matter are the two that I've shown. So the first is just basically two copies of the original Euclidean black hole. Okay, so this disk is a Euclidean black hole that I showed a few slides ago, and we just have two disconnected copies of it. This is sort of, the thing that's going to give you the naive Hawking answer. Okay, so so what answer does this give you? Well, the first thing to note is that here we have an end of the world brane that starts in state j, and then over here it's in state I. Okay, so that tells you that this sort of double sum over I and j, only the diagonal terms contribute. You need to have I equal to j. Okay, so that means we're doing this sum, we only get one factor of k. We had a 1 over k squared out here. So the final answer ends up being suppressed by 1 over k. And in fact, that's the exact answer because these Euclidean black holes cancel between the sort of the ones here that we're interested in and the ones in the denominator that come from normalizing our density matrices. Okay, so this answer for trace rho squared equals 1 over k, that's analogous to the entanglement entropy being given by log k. But there's another boundary, another topology that we need to consider. And that's this one over here, where we have the two black holes, but they're connected together. They're connected together by a Euclidean space-time wormhole. What does this mean? Well, the first thing to note is that the sort of gravitational action associated with this thing is much, much smaller. Sorry, the action is much, much bigger, and so the e to the minus action is much, much smaller. Why is that? Well, in 1 + 1, 2 dimensions, then the sort of Einstein-Hilbert action is just given, according to Gauss-Bonnet theorem, by the Euler characteristic of the manifold. It's just a topological invariant. Okay, what is the Euler characteristic of this? Well, it's one disk, which has Euler characteristic 1. So this thing has an action that looks like e to the s. But as I said before, in the denominator, we have 2 Euclidean black holes, has an Euler characteristic 2. So we've got to divide through by e to the 2s. We end up with e to the minus s naught. Okay, s naught here is the term in front of the Einstein-Hilbert action. But roughly speaking, in 2-dimensional gravity, it's the sort of 0 energy Bekenstein-Hawking. So this this Euclidean wormhole is very, very suppressed. It doesn't want to exist. It's like an instanton effect. It's non-perturbatively suppressed. But when we do this double sum over I and j, then there's no longer any reason that I needs to be equal to j, because these two end of the world brains got connected together through the Euclidean wormhole, and these two did. And so there's no end of the world brain that connects an I to the j and enforces them to be the same. That means we get a factor of k squared from this sum, cancels out the 1 over k squared, and we get an answer that does not decay even as we take sort of k to infinity. Okay, so even though this is a tiny, tiny, tiny thing, if we make k big enough, bigger than e to the s naught, then it still becomes the dominant contribution, because this sort of naive one becomes so, so small. Okay, so that is, you know, trace rho squared being equal to e to the minus s naught at very, very large k is like a big hint that our entanglement entropy is actually saturating at the Bekenstein-Hawking. But, you know, that's okay, that's fine, but we're really interested in the von Neumann entropy. Renyi entropies are sort of weird things. They're very sensitive to, very non-continuous as a function of the states and stuff like that, have some nasty properties. So we want to calculate von Neumann. So to do that, we need to sort of evaluate trace of rho to the n for all values of n. In general, there's quite a lot of topologies that can contribute. They're related to something called non-crossing partitions, which I won't really have time to talk about much. But in the limit where sort of either k is sufficiently small or it's sufficiently large, then there will just be one family of topologies that dominates for all values of n. So what are these topologies? Well, for small k, then they're just n independent Euclidean black holes. Okay. So what answer does this give? Well, again, the gravitational action cancels between top and bottom. And so we're just left with an answer of 1 over k to the n minus 1, because we have n different like i's, ij, so on, n of them, and they're all being forced to be equal. And in the normalization, we have 1 over k to the n, so that gives us 1 over k to the n minus 1. So if this is for values of k where this is the dominant answer, we can take its log, divide by n minus 1, we get log k, analytically continue log k as a function of n, and you just get log k. So this gives indeed an entanglement entropy equal to log k. This is the naive answer, but the point is that it only dominates when k is much smaller than e to the s. What about when k becomes really, really, really large? Well, now the gravitational path integral is dominated by topologies where no end of the world brain gets connected to an end of the world brain with a sort of different label. Okay, so they can all be independent and you don't have this suppression by 1 over k. What is the leading thing that gives that? Well, again, it's just sort of one disk where all these black holes are connected together by a multi-boundary Euclidean wormhole. So just to the level of topology, this gives an answer of sort of, has Euler characteristic 1, normalization has Euler characteristic n. So we get an answer of e to the minus n minus 1 s naught, log, divide by n minus 1, analytically continue, and we get that the topological contribution to the entanglement entropy is just s naught. Okay, so this is a good hint that we're going to get the Bekenstein-Hawking entropy of the black hole. But we can do better. And the easiest way to do better is to use a trick that was introduced by Lukowitz and Maldacena back in 2013, I think, for deriving the so-called Ryutakyanagi formula. And that's the following. you know that this sort of connected topology has a symmetry. It has a Zn symmetry where we sort of rotate these n copies around. So what we can do is we can just quotient by this symmetry and just look at one of these wedges here, okay? And then we this line here gets glued to this line down here. So now we've ended up with something that sort of looks like the original Euclidean black hole, except that there's this conical singularity that's sitting here where we glued this line to this line. That conical singularity is at the point that was the fixed point of this replica symmetry that moved the different copies around. Now, when we consider the quotient geometry, there's no reason that we have to consider integer n. We can just consider analytically continuing to non-integer n by just changing the strength of this conical singularity. So we take the limit n goes to 1, then the conical singularity goes away, and we get back the Euclidean black hole. Okay, we get back this original unback-reacted Euclidean geometry. But in the limit that it's very, very close to 1, then you end up getting a contribution to the von Neumann entropy, which is just given by the area of this fixed point. In this case, the fixed point ends up being the bifurcation surface of the black hole. In 2D gravity, the area is really the dilaton. And so we get an answer that's the value of the dilaton at the bifurcation surface of the black hole. That's the Bekenstein. Okay, so that's the story of how you calculate the von Neumann entropy, and you get this right answer that it is given by the smaller of log k, the sort of naive amount of entanglement entropy, and the Bekenstein-Hawking entropy, as we hoped from unitarity. Now I want to talk a bit about how you can actually see that information can somehow be extracted from the interior when we sort of go to this regime where we're effectively after the page time. So the way you do that.
Can
Yep.
I ask a question? So I know that, like you're trying to calculate the von Neumann entropy. I was wondering, if you are instead trying to calculate some kind of a correlator, would there be a shift in the saddle point in a similar way, or would the
what sort of correlator are you thinking of? Just sort of like a simple like correlation function in the Hawking radiation or something like that?
Yeah, some boundary.
So no. The answer is that if some simple Hawking radiation observable, then the dominant saddle point will still be would just be the ordinary Hawking saddle, and you'll get an answer that's this sort of answer you would get if things were thermal. But that's fine, because if you have unitarity, like in simple sort of scrambling time models, then it's still true that simple like endpoint correlation functions do look thermal. So that's actually the right answer both for information loss and non-information loss.
Mm-hmm. So what kind of a correlation function would pick up this saddle point? Is there some? So
very complicated ones.
Yeah.
Correlation functions of reconstructions of the interior, which is what I'm going to talk about right now.
Okay.
But those reconstructions are themselves sort of very, very complicated, exponentially complicated operators.
Okay. Thanks.
Okay. So yeah, the way we're going to construct these reconstructions using just a general purpose tool from sort of the theory of quantum error correction that's called the PETS map. So how does this PETS map reconstruction work? Well, it basically involves sort of simulating, your quantum computer or whatever's doing the reconstruction, simulating the black hole evaporation process, or in this case, simulating a construction of this state with a large amount of entanglement between interior and exterior. Okay, so then what ends up happening, and this is totally crazy, and the question of how literally to take it, I think, is an open one, is that when you do the calculation, then you end up, it's very natural to consider space-time wormholes that connect the sort of real black hole that you're trying to reconstruct information from to the simulation of the black hole that you're using to define your reconstruction. So when you include these things, then then what happens is that if you're after the page time, and only if you're after, then the sort of dominant configuration is a wormhole that connects together the real black hole to the simulation in the quantum computer. And this simulation in the, so what that wormhole sort of pulls out the information in the interior that you're trying to reconstruct, and then does something to it in the quantum information, the simulated black hole. It either measures it, or it like, you know, manipulates it if you're trying to reconstruct some unitary operator. It does the thing you're trying to do to it. And so, yeah, you can do these calculations, and they say very precisely that if and only if you're after the page time, then you can in fact learn about the interior of the black hole by doing these very complicated things.
Sorry, degrees of freedom you use for this black hole simulation, are these the Hawking radiation degrees of freedom?
So the operator is an operator on the Hawking radiation, but this is a general purpose tool for doing error correction, right? So it needs some input about the thing you're trying to error correct, right? That input is effectively a simulation of another copy of the black hole, okay? And then when you do the path integral, if you include wormholes that connect that sort of simulated copy of the black hole to the actual real black hole, then you get this sort of right answer that after the page time, this general purpose reconstruction does its job and manages to reconstruct the interior. And if you're before the page time, it doesn't. So yeah,
sorry, just to understand. So you're looking at an operator, and
yep.
the definition of the operator is the simulation, whatever, but the operator acts on the Hawking radiation degrees of freedom.
Yeah, exactly. Yeah.
Thank you.
So it's not defined as just like a load of sigma matrices or something, just some fixed thing, because obviously, you know, that can't work as a general purpose reconstruction. It's more like, you know, yeah, you apply the Pauli matrices on the Hawking radiation that you apply depend on you know, the dynamics of the black hole, and are defined using the dynamics of the black hole. Okay, and then that thing that you're using it to define it can get connected. Okay, I should say that even that story, crazy though it sounds, and I'm sorry I'm not going to have time to really go into this story properly and give the maths, because it is sort of, the maths is the most compelling part of it. Without that, it just sounds totally crazy. The story I gave on the last slide was sort of oversimplified. And in fact, just like when you're calculating the von Neumann entropy, when you're really calculating this sort of PETS map thing, then you have to do an analytic continuation. And effectively in the analytic continuation, the sort of total number of simulated black holes ends up going to 0. So it's sort of like the von Neumann entropy, you end up with just one black hole. In this one, you end up with just one black hole, which is a real black hole, plus like 0 simulated black holes. But because of the way you do the analytic continuation, then you still get this answer that includes contributions from space-time.
Sorry, so is the end result that you have an operator acting on the Hawking radiation degrees of freedom?
Yes.
That effectively reconstructs a local operator inside the black hole?
Yes. That's accurate. Yeah. So yeah, if you're actually like an actual physical person, and you're sort of trying to like, you know, use a physical quantum computer to pull out this information, then you can't analytically continue the circuit that you use, right? That's just a mathematical trick. Like it works by definition to give the answer. But if you're actually trying to use sort of simple unitary gates to construct this circuit, then you have to do something different. And the actual way that you have to do it uses something called Grover search. And in fact, effectively what you're having to do is simulate the black hole exponentially many times. So this is discussed in a paper I put out with Adam Brown, Grant Garabian, and Lenny Siskind called The Python's Lunch. But the real takeaway is that if you actually want to extract information, you know, reconstruct a local operator in the interior using the Hawking radiation, then you need to do something very, 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 very complicated, like unbelievably complicated. Not, you know, the entropy of a black hole is, solar black hole is like 10 to the 70 something. So this is the number of gates you're applying in your quantum computer is like e to the 10 to the 7th. Insanely high. So
can I ask a question, please?
Yep.
Hi. Will this argument actually also apply to a piece of coal that is burning, that you can reconstruct the piece of coal in terms of?
So it will be true that the PETS map would work for the piece of coal. You know, the PETS map will work pretty much whenever anything will work. It's sort of built to do that. That's literally its job. You know, the calculation with the piece of coal will not involve an interior. It will not involve like wormholes connecting together to interiors. Now you can question how we should interpret this calculation, but it is indisputable that the calculation gives the right answer and involves this information being in a smooth interior, and then that smooth interior getting because of just dynamical quantum gravity effects getting connected through a space-time wormhole to this exterior simulating system.
Okay.
So yeah, even if Hawking was sort of wrong from a sort of Shannon theory point of view, from the information theory point of view, then from sort of a computational complexity point of view, he was totally right. As a practical matter, then information that falls into the black hole is just lost. And this is also true of a piece of coal, though I think it's probably more true of a black hole. The entropy is a lot bigger for a start. But yeah.
Sorry, could I ask
practical matters? Yeah, sorry, go ahead.
Could I ask what's probably a stupid question? Suppose I have your black hole, and now I throw something in. Okay, so the inside of the black hole changes. Now, the Hawking radiation degrees of freedom were very far away or disconnected as in your model, so they haven't seen that it's fallen in. So the reconstruction that you do with your Hawking radiation degrees of freedom produces the inside of the undeformed black hole. But actually now the black hole has changed because you throw something in. So how's this consistent?
Yeah, the answer is it doesn't. And it doesn't because, the thing that falls in gets pulled out through this space-time wormhole. So if it hasn't fallen in, it won't be pulled out, and you'll get a different answer for this operator. Is that clear?
Okay, so you say that the operation acting on degrees of freedom that are very far away knows that you've thrown something in an almost acausal manner.
Yep.
Okay.
Each individual saddle is it's within the saddle, it is local, but these space-time wormholes are very non-local objects, right? They connect distance regions of space-time. So
I'm sorry to go on, but one more question. Of course, the Hawking radiation degrees of freedom have not been acausally affected by your throwing something in, right? So what has changed, I suppose has changed is the definition of the operator that you need to put. That has to change immediately.
So there's two separate questions. There's if you're just trying to measure whether the thing has fallen in or not, then you can use one operator that will tell you which of those two things happened. But there's then a thing of like, if the geometry of the interior is changed by the operator, then sort of how the operators. Okay, here's the right statement to make. All these operators are only defined to work within a certain code subspace of possible states. Okay, so if you defined your reconstruction operator to work regardless of whether that particular thing is thrown in or not, then it will work regardless of whether it's thrown in or not. But if you try to use a PETS map based on a code subspace that does not have that thing being thrown in, then you will just get nonsense answers if you try to use it and something has been thrown.
So the way that the causality works is that you have to change the definition of the operator because you've thrown something
except you could use one operator that works for both. Yeah, you can. Yeah.
Sorry.
Yeah, go ahead.
Sorry, Shazbir, why do you want to insist on causality? I mean, the whole point here is that if you look at very complicated operators, the notion of causality needs to be refined. If you insist on
I'm not trying to insist on causality. I didn't think.
I thought causality was an exact property of string theory S matrices, for instance.
But what you're talking about is bulk causality. You're not talking about, it's a different thing to say that you look at asymptotic operators and they commute exactly at space-like separation, which is what the S matrix gives you. But now what you're saying is you have some object in the interior and you want that to commute with something outside. And that's not even true perturbatively. Even perturbation theory, that won't happen.
Okay, but then you're going to have to find, I'm sorry, I'll stop talking after this, but then you're going to have to find a way that makes this violation of causality consistent with the causality of the S matrix of gravity, and that.
Because the causality of the S matrix is a statement of asymptotic operators commuting exactly, which is true. And this is a statement about complicated operators asymptotically knowing about some simple operator in the bulk, which is also true. I mean, there's no I think contradiction between those statements.
Maybe there's no contradiction, but they sound like they're at least naively intentioned. You're going to have a hard time putting them all completely together.
I say, even in perturbation theory, you will see this effect. I mean, it's a small effect in the operators that we are looking at here. They're very complicated operators, so the effect is scaled up to order 1. But even in perturbation theory, you'll see 1 over n effects of this loss of causality, which you just can't get rid of.
But all of Geoff's calculations are in Euclidean theory, right? So somehow this discussion of Suvrat and Shiraz is about Lorenzen. So this translation.
You can certainly, in the richer theories where you actually have Hawking radiation, then there's certainly Lorentzian dynamics going on. But it's also true that fundamentally, you're doing like a complexified contour, but it's always, in any of these calculations, there's sort of implicitly at least a bit of Euclidean stuff going on. You're not just calculating the S matrix or something like that.
Right.
So in that sense, it's the question of finding a unitary S matrix and like actually seeing what the S matrix is directly is like not answered by these calculations. Maybe I should go ahead because I still have quite a bit I'd like to talk about.
Sorry.
No, totally fine. It was interesting discussion, but just a few final quick comments about this toy model. One of the nice things about it is that we, as I say, we don't have to resort to just looking at classical saddle points. We can actually just do the full path integral. And more than that, we can do the full path integral and include all the relevant topologies, even near the transition. And then you can use tools from free probability theory, and you can actually find the non-perturbative corrections to the von Neumann entropy that happen near the transition. And in fact, you can get the full entanglement spectrum of the Hawking radiation near the transition. Answer ends up being complicated. There's sort of 7 distinct subphases as you go through this page transition. But the sort of overall answers you get are what basically people expected already. In particular, you end up with an enhancement to the corrections near the page time that basically comes from energy fluctuation. But I don't want to get too much into that because I want to talk for as long as I have, a bit short on time, about like how this relates to actual evaporating black holes. So this is mostly going to be getting back to my paper in May. So what can we say about actual evaporating black holes? Well, the bad news is that no one has found an analytic replica wormhole saddle point at sort of integer n in any more realistic model than the one I just showed you. We have numerical saddle points in the SYK model, and in fact, these suggest that the physics of what's going on is just inherently messy. You have complicated back reaction, the sort of fast scrambling effects are coming into play. It's just some sort of ugly complicated. But the good news is that we saw in the simple model that the sort of von Neumann entropy ended up being, at least not near the transition, being controlled by just the area of this replica fixed point just in the original unback reactive geometry. So all the complicated back reaction and stuff you had for higher n just ends up being completely irrelevant. It turns out this is generally true for all the sort of replica wormhole entropy calculations, and in fact, it's also true for the PETS map calculation. In both cases, it's because you really end up with a limit where there's only one copy, and so it ends up not being back reacted. Okay, so let's sort of understand what the story is. I'll just state it. I won't derive it that well. But basically what happens is that you can show in this sort of limit where n gets very close to 1, that the replica fixed point needs to be what's called a quantum extremal surface. So what is that? It's an extremum of this quantity in the square brackets called generalized entropy. It's just a sum of area plus 4g Newton, which is all we had before because we didn't have any bulk fields, plus this sort of quantum correction to the area, which is just the entanglement of the bulk fields across the two sides of the surface. Okay, so the replica fixed point is a quantum extremal surface. Then, for any given replica fixed point, then the sort of von Neumann entropy you would get by analytically continuing that family of saddles ends up just being the generalized entropy of the corresponding quantum extremal surface, the quantum extremal surface that happens to be the replica fixed point for those saddles. Okay, and the final point is you need to know which family of saddles are the like dominant ones that give the right analytic continuation, dominate the replica trick, and they're just, this is maybe slightly sloppy, but the correct statement is that they're the ones that come from the replica fixed point with the smallest generalized entropy. It's called the minimal quantum extremal surface. Okay, so the rule is you look for all the quantum extremal surfaces, you take the one with smallest generalized entropy, and then the final answer for the entanglement entropy is just that generalized entropy. So this is sort of the quantum generalization from Engelhardt and Moore of the Ryo Takinagi or Hubini-Rangamani Takinagi formulas. Okay, so how does this apply to sort of actual evaporating black holes? Well, in the toy model for small k, the dominant saddle points for the replica trick were just disconnected, right? So that means there's sort of no replica fixed point. Just there's nothing connecting the different copies together. So even for an evaporating black hole, we also have a quantum extremal surface that corresponds to having no replica fixed point. It's just the quantum extremal surface that consists of the empty set. Okay. So what is the area of the empty set? Well, it's 0. That's easy. What about this sort of S bulk term? Well, it's just the sort of entanglement between this sort of blue region and these green Hawking modes that escaped off to infinity. What is that entanglement? Well, this is just the Hawking calculation, right? So this is just something that grows linearly with time, given by the sort of thermal entropy of Hawking radiation. Okay, so this empty quantum extremal surface gives you a generalized entropy that's just the semi-classical entropy of the Hawking radiation. So this gives the Hawking answer, and it turns out that before the page time, this is indeed the minimal quantum extremal surface, and so this is the right answer. This is sort of the first half of the page. But it turns out that there also exists another quantum extremal surface, a non-empty quantum extremal surface that lies just inside the event horizon of the black hole. This yellow dot in the Penrose diagram. Really, of course, it's a sphere. What's the area of this surface? Well, it's just the horizon area. What about the entanglement entropy of this surface, S bulk? Well, the sort of huge amount of entanglement is between these green modes here and their interior partners down here. And those are now sort of on the same side of the surface in yellow, right? They're both in green. And so they don't contribute to the entanglement entropy. The entanglement entropy is just the entanglement across this surface, and that ends up just being small. It's just some order 1 subleading correction. So leading order, the generalized entropy of this surface is just the Bekenstein-Hawking entropy of the black hole. After the page time, the Bekenstein-Hawking entropy of the black hole is smaller than the semi-classical entropy of the radiation, and this becomes the minimal quantum extreme. So this is the sort of indication that there's a transition going on in the replica trick to these fully connected replica wormhole topologies, even though the actual replica wormhole topologies are too complicated to calculate. These more realistic models. As we allow the black hole to evaporate, as we include more and more Hawking modes in our escape radiation, then this RT surface just sort of tracks along the horizon. It moves in a space-like trajectory that sort of gets closer and closer to the horizon, like Gorn. Because the black hole is evaporating, that means that the generalized entropy of the surface decreases with time. And so we get the second half of the page curve where the entanglement entropy just steadily decreases. Okay. What about if we throw a diary into the black hole? And throw it in after the page time, because that's the more interesting case. Initially, the world line of the diary looks something like this. It's going to go through this blue region. Okay, it's going to be going to the right of this yellow dot that's quantum extreme. That means that there's sort of no way it gets connected through one of these replica wormholes. If we try to use the PETS map to reconstruct it, then we wouldn't be able to pull it out through a wormhole and then measure it or whatever. And so the PETS map can't learn anything about this diary. No information about the diary has escaped it. The technical term is that it's still in the entanglement wedge of the black hole, not the entanglement wedge of the radiation. I want to avoid using that term, so I don't want to define it. However, as we let the black hole continue to evaporate, i.e. we sort of allow ourselves to act on more Hawking radiation, we treat more Hawking radiation as having escaped to infinity, then the quantum extremal surface moves along the horizon. The world line of the diary stays in exactly the same place, but it turns out that once we've waited for more than something called the scrambling time, once we've extracted more than the scrambling time's worth of extra radiation, then the world line of the diary is now in the green region rather than the blue region. This is the now in the entanglement wedge of the Hawking radiation. It's in the so-called island. It represents the fact that this entanglement wedge is sort of a blob is in space-time that doesn't get connected to any boundary. It's called become known as an island. What does this mean? It means that the information of the diary can now be pulled out through a wormhole by the PETS map, and we can work out what the state of the diary was by doing a measurement. So information has escaped. So this is exactly reproducing a famous prediction by my advisor Patrick Hayden and John Preskill. But they made it based on just sort of simple toy models of like black holes as chaotic quantum systems. In this case, we're getting exactly the same answer up to the linear coefficient, just from a gravity calculation. Okay, what about the famous firewall paradox? So what does this say? It says, let's consider this late time Hawking mode here that's about to escape. That, if the page curve is true, then that late time Hawking mode needs to be entangled with the earlier radiation, so that moving it across will decrease the entanglement entropy of the radiation. But for the horizon to be smooth and be a low energy state, then that mode needs to be entangled with its partner mode in the interior. However, monogamy of entanglement says that one thing can't be highly entangled with two different things at once. So how do we resolve this paradox? Well, it's very simple. We just evolve that interior partner mode back in time, back to here, and we notice that it's in this green region. What does that mean? It means that it's in the entanglement wedge of the Hawking radiation, so it's secretly actually encoded as a complicated operator in the early Hawking radiation. This is the so-called ER equals EPR or A equals RB resolution to the firewall paradox. But again, we're deriving it from gravitational calculations. PETS map shows that you can extract out this mode into the Hawking radiation, and then in gravity, that mode will just no longer be there in the interior. So we have no paradox, everything works. Again, the full story is much, much more complicated than what I've told you. This is sort of a very heuristic picture where we have these sort of modes and they're entangled with each other. There's a couple of important subtleties. The first is that this thing isn't exactly entangled, perfectly entangled with the early radiation, because that would actually make the entanglement entry go down too fast. It just needs to be mostly entangled with it and a bit entangled with the black hole. And the other is that this interior mode is sort of delocalized. It's a Windler mode, and so it's not perfectly in the green region. It's like partly in the green region, partly in the blue. Magically, and this to me is the most like beautiful and compelling part of the whole story, to be honest, the fact that this yellow surface is a quantum extremal surface magically makes those two corrections be exactly the same as one another. So everything perfectly works out, and you exactly avoid a firewall paradox or sort of a reverse firewall paradox of like the interior not being enough entanglement between the early and late radiation. Yeah, it's a really beautiful story. I think it's really, really cool, but I'm not going to have time to go into details. It's in my paper from May. So this is all great. But even though that sort of explains how to resolve the firewall paradox, in many ways, it still hasn't explained how to resolve the information paradox, even though we claim you can do these calculations to show information getting out. Why is that? Well, it's because so far we haven't actually given a mechanism by which there's any influence on the sort of combined state of all this radiation from the matter that fell in down here. So let me be more precise about why this is true. It's not enough to sort of not have a firewall, that there be entanglement between this mode and the Hawking interior partner. It has to be entanglement in a particular entangled state, right? The thermofield double state, basically. So just to have the sort of low energy state near the horizon, we need to have a fixed state on Hawking mode's tensor interior part. That state cannot depend in any way on the matter that fell in. Hence, even if the interior partner is secretly an operator that acts on the early Hawking radiation, then there's still no way that sort of adding this extra quanta of Hawking radiation to the early Hawking radiation can teach you anything new about the matter that fell in, right? Because it's just entangled with some fixed operator on all this stuff, then it's the overall state is fixed. Even if the entropy is going down, then you're just ending up with some fixed state of the Hawking radiation that doesn't depend at all on anything. And the reason for this is that we're sort of missing the final piece of the puzzle, which is state dependence. So this was sort of, the idea of state dependence in black hole interiors was developed primarily by Suvrat and Papadopoulos over a number of years. But I'm going to be talking about a sort of maybe minimally ambitious or radical statement of state dependence, which is just state-dependent quantum error correction. Okay, so what is that? I earlier claimed that anything that's in this green region is encoded in the radiation after the page. That was technically a lie. The true claim is that any small subsystem that was thrown in is decoded in the radiation, provided you know the state of everything else that fell into the black hole. I.e., you can find an operator on here that like does whatever you want or measures whatever you want about this operator, but it will only work provided the state of everything else that fell in is fixed. And the operator that you have to use depends on the state of everything else that fell in. If you don't know that the state lies in this sort of sufficiently small code space, then when you try to create a space-time wormhole using the PETS map, it just won't work. The PETS map is different for different subspaces. If you try to use it for too big a subspace, then you just won't be able to make the wormholes connect. The dominant contribution will come from disconnected saddles, and you just won't get the right answer. So what does that mean? It means the encoding of this operator in the Hawking radiation depends on the state of everything else that fell in. However, as the black hole continues to evaporate, then you can make the PETS map work for larger and larger subspaces. basically because the difference in generalized entropy between this non-empty quantum extremal surface and the empty quantum extremal surface gets bigger and bigger. So you sort of have more, more margin of safety to make the more margin to still have the connected wormhole saddles dominate over the disconnected saddles. Eventually, you don't need any prior knowledge of what was thrown in at all. All the information about the initial state of the black hole has escaped. Interesting fact, this actually happens even while the black hole is still semi-classically large. It happens when the black hole is about 90% evaporated. And that's just because black hole evaporation is an thermodynamically irreversible process. Okay, so how does this resolve the sort of version of the information paradox I introduced a couple of slides? Okay, this late time Hawking mode in the interior, this late time Hawking mode here is indeed entangled with its interior partner in this fixed vacuum, or thermofield double, whatever you want to call it, state. Okay, and that does not depend on the matter that fell in down here, just as Hawking predicted. However, the encoding of this interior mode in this stuff over here, in the early Hawking radiation that escaped to the boundary, does depend on the stuff that fell in. Follows that the combined state of late radiation plus early radiation can depend on the state of the stuff that fell in, because the type of entanglement you have between early and late radiation depends on the stuff that fell in. It's like if you sort of have two encodings of the same message. If they're encoded in different ways, then you can still learn information from them, from like looking at them, even though they have the same message as one another. That's because you're learning information about the code that was used in each case, right? So even though you know the encoded the plain text message, you don't know what the encoded message looks like, and so you can learn information by seeing what the encoded message looks like. So everything's consistent with information getting out. That does not mean that this argument tells you precisely that it will get out, but we do have the calculations showing that the information stuff that fell in can get pulled out by PETS maps and so on. So it's certainly consistent with that. Okay, so I'm a bit over time, so I'll just make some brief final comments. So one thing I didn't have time to talk about before, but is sort of something that appeals to me as sort of having a more quantum information background, is that this whole story is only possible, like the story with the state dependence and so on, is actually only possible because the error correction involved, the reconstructions using the PETS map, are only approximate. There are non-perturbatively small errors in them that just are inevitably there and can't be got rid of. They come from these other settings. And the reason for that is that basically approximate and exact quantum error correction behave very differently when you look at very, very large Hilbert spaces. The sort of limit epsilon going to 0 and the limit where the Hilbert space dimension goes to infinity don't commute with each other. Semi-classical limit is the limit where the Hilbert space dimension of the black hole microstates goes to infinity. So yeah, it's unsurprising that there should be subtleties there. Another comment is that the results I discussed are consistent with a single unitary theory of black hole evaporation, but they're also consistent with the gravity calculations being an average over an ensemble of unitary theory. And in fact, the sort of very simple toy model I introduced, that is a non-perturbatively complete theory that has a sort of boundary dual, but it's an ensemble boundary dual where the gravity calculations are calculating an average over the ensemble of theories on the boundary. There's very good reasons to believe that sort of higher dimensional, more complicated theories of quantum gravity, such as n equals 4 CPM Mills, string theory on ADS5 cross S5, are dual to a sort of single unitary theory, n equals 4 CPM Mills. But there's still some questions about how this can be sort of fully consistent with a fundamental theory that contains space-time wormholes. You either need to sort of have miraculous cancellations, or the space-time wormholes just need to sort of be an emergent low-energy phenomenon. There's various options, but yeah, I don't think it's fully understood what the right one is, or even, I'm not sure how we would know without talking about a specific theory of quantum gravity. So there's a lot of interesting questions left to answer. I think it's a really exciting progress being made all the time, and I look forward to seeing where it goes next. So thank you.
Oh, great. Thanks, Geoff, a lot for the very interesting talk. So maybe we can mute our microphone and clap up to show our appreciation to Geoff. Okay, so now we have some time for questions. So if you have any questions, comments, please go ahead.
I have a question.
Yeah.
So the question is, in your discussion of the evaporating black hole, if I understood correctly, you were largely thinking of an ADS, a large ADS black hole coupled to an external reservoir.
In the slides in this talk, I made it be in asymptotically flat space because the story is basically the same. But I think the most precise case is that. Yeah.
Right. No, so I want to question the issue of whether asymptotically flat space is the same, because there's another way in which you could think about an evaporating black hole. And just to come back to ADS CFT, and that is to think of a small black hole evaporating in ADS. If you were to think of a small black hole, then in fact, the page time or the page curve would not necessarily be so significant. I mean, I don't know how to think of in terms of information recovery, because you might have thought that for a small black hole evaporating, if you looked at sufficiently complicated operators near the boundary, they might always know about the interior. So I was wondering how you think about a small black hole. So sense of why the page time might be important.
I would distinguish between operators. Look, with operators at the asymptotic boundary, sort of all operators, then you have everything. Fine. And I'm very happy. I know your paper on the asymptotically flat space and wanting to argue that works the same way as ADS. I completely agree that that's very plausible. That's how it should work out. But it seems to me that's different from the question of the information that is encoded if you just look at the Hawking modes themselves, right? That is not, just looking at the Hawking modes is different from looking at all the fields at asymptotic infinity.
Let's say, I mean, I would think there's, one could...
Here's a story about small ADS black holes. You start with that small ADS black hole evaporating, and then you just use HKLO style reconstructions to just pull out the Hawking modes for up to some time before the page time, extract them into a separate system. Then I think it would be true that you just see that they're in a thermal state, and that entropy would be the entropy it would be.
So maybe one way,
that isn't inconsistent with the fact that at the boundary, then everything is fundamentally encoded in the asymptotic boundary.
Right. So maybe one way to make this precise, and maybe that's what you're trying to get at, is one could try and ask, what are the observables for which you would see the page curve? So I mean, one way you could say is, let's look at k point correlators, and we'll set k as we like, so that you see the page curve. Now the concern is that you need to set k in such a way that at intermediate times when the black hole exists, you don't get all information. But you need to keep this k large enough that at late times you do get all the information. So the issue is somehow that you need a probe of the system that is able to extract information at late times and is not able to extract information at early times. And the concern is that that's not quite consistent with the intuition you'd have from thermalization, because if you try to look at S point correlators, they might have information at all times. Do you see what I'm saying? Just think of this process on the boundary. You have the formation of some quark-gluon plasma, and then it evaporates into some set of glue balls. And if you probed it with sufficiently complicated operators, you could always detect the state. And what is being suggested, somehow the page curve would suggest that there's some sense in which it becomes easier to recover the information at late times, which runs opposite to the intuition we have from thermalization. Do
I
you
don't
see the
think
question?
it's no. Yeah, I don't think it's about the time. Look, let's say even for a small black hole, I can just extract a single Hawking quantum, right? Let's extract it into an external system for concreteness. Right?
Sure. Okay.
Would you agree that when you do that, then that Hawking quantum will be in a mixed state?
Absolutely. Yes.
And then I keep extract another one, becomes more mixed, and so on. Would you agree if I keep doing that for all the quanta, even though it was a small ADS black hole, then I'd get a page?
So you have to. So the question is, does the observer get to measure k point correlators at like s point correlators at all times, early times and late times? If the observer has the power to measure like s point correlators at all times, then he sees then I think he doesn't see the page curve. And if you limit the observer to less than point correlators, then he just sees the Hawking curve.
So I don't want to think about it in terms of, let's just think about the sort of replica trick definition. Let's just apply a swap operator to some large number of Hawking quanta. Like we have two copies of the system and we swap Hawking quanta between two pairs and we look at the expectation of that particular correlation function. What would you expect that function to look like? If we have like an order 1 number, then it will clearly be like e to the minus the thermal entropy.
I didn't understand this.
Maybe can I annotate. So we have, let's make them be asymptotically flat. We have two black holes. And then we have some modes coming out here. And we just measure, the correlation function we measure is just swap on these two, tensor swap on these two. Swap operator you can just write as a sum over correlation function, like operators on the two sides if you want. But it's just a Hermitian operator that acts on those two things. And we just take a product over a load of them. And then we take log of the expectation of the swap operator. So this is the Rainy 2 entropy. And the question is, what curve will that follow?
Log of the expectation. Is this just this is a 2-point function of ordinary operators, not of ordinary operators?
Well, it's a higher point function because it's a swap on these two, tensor a swap on these two, tensor a swap. You're swapping each of the quanta.
Right. So it's a very high
but
point.
It's not some. It's a high correlator, but it's not that complicated an operator.
Okay.
I still think there's a distinction between the information that's in the Hawking modes and the information that's in sort of all the fields at asymptotic infinity.
Yeah, I should let other people ask questions. We can return to this. Sure. Yeah.
Okay. Let me make my final comment. In flat space, you guys talk about how all the information is encoded down here, but it's not necessarily encoded here, right?
Right.
If I plot the entropy of a state as a function of it going up here,
right,
would you not expect to see the page curve?
No, because if you mean one segment is always fixed at the pass boundary of null infinity, and the other segment.
No, I'm just saying about one copy now. You look at just the entropy of the state up here. What would you'd expect? Presumably that would be non-zero, right? At least initially. Like some Hawking quanta escape.
Yes, I want to understand how this is the state defined on the segment where one copy always ends up at the pass boundary of null infinity, or is the state defined with a moving segment that just moves?
Make it a moving, make it a moving segment. I do.
A moving segment.
I wouldn't have said you even need a segment, right? Because it's You want to say that all the information is in a small interval down here, right?
That's right.
So
as
then
you
now
go up,
consider a small interval up here.
so if you go, so now you want to look at a small interval that's up higher somewhere.
Yeah.
Well, that's yeah. That kind of thing might obey some kind of a page curve. You mean? I mean, there's the issue of how soft and hard modes are entangled in 4 dimensions. But you're right.
Yeah.
It's kind of the reverse page curve. It's but yeah, you might have thought that kind of that what you're really looking at is some segment which is anchored at the future boundary of null infinity and then extends down, and then you shorten it. I mean, this moving segment I think captures that. So I don't know how the soft hard entangle, but yeah, modulo some issues of that might obey some kind of a page curve. But is this what is physically being measured here by this? Like the entanglement of a short segment?
Well, what it's really measuring is the expectation value of these swap operators, or an analytically continued version of that.
Okay.
And that is computing. Yeah, that's computing the entropy of the right moving modes, the outgoing modes at asymptotic infinity.
Okay.
But I didn't think those contain everything. Anyway,
Okay, yeah. Thanks.
Cool.
Any other questions?
Sorry, a question, please. Suppose you had a black hole that was formed by the collapse of a particular scalar a collapse of a scalar field in a given profile. So I give you classical initial conditions for the scalar field, and I let it collapse.
Yep.
And when in the end the black hole has, I wait for it to eventually radiate, to Hawking radiate. In the end, the black hole has evaporated. Now I want to find a formula for the quantum state of the gravitons and the scalars eventually. Now Hawking gave us some sort of formula. And I wanted to ask whether, given your new insights, whether it's possible to actually carry through this calculation.
Yeah, no, is the short answer. That's the big thing that's missing. You can calculate. Here's the things you can calculate. You can calculate like simple correlation functions on the final state, and the answer is that they just look thermal. Like there's the same answer Hawking would have given. You can also calculate the entropy of that final state, and you find that it's pure. I mean, slightly, there's the issue with the black hole, the final part of the evaporation, then it you don't have good semi-classical control over it. But at least if you let it like 99% evaporate, then the entropy ends up being equal to the Bekenstein-Hawking. It's much smaller than Hawking would have said. So that is again something you can calculate. But you can calculate it fundamentally because it's related to this relatively simple correlation function. This thing, it's like it's an S-point correlation function, but it's like a product correlation function. To actually determine the state, like which pure state it is, then you need to be considering like exponentially complicated correlation functions, and those are just very hard. Here's another way of saying the same thing. Let's say you want to compute the full like density matrix of the output, right? And see whether it's pure or not. For any individual density matrix element, then you can compute that. And what you will compute is you'll get Hawking's answer plus like, you'd expect there to be non-perturbatively small e to the minus s corrections, right? Just because there were always going to be. You don't have good control over what those are. But now if you look at, it's a tiny effect doesn't really matter. Up to tiny corrections, then the answer is what it is. But now let's say you want to actually get the whole density matrix to some good approximation, right? Even though you can work out every single matrix element up to e to the minus s error, then because the density matrix itself is size e to the s by e to the s, that does not give you any control over the density matrix in terms of like the trace norm or whatever. So you just don't have a good ability to work out what the actual final state is. Is that clear?
Okay. I was hoping for some sort of path integral representation of the unitary evolution operator that included some sort of wormholes. Then maybe evaluating it would be tough. But that's not possible.
There's no. I mean, and one way to answer this is that, you know, the really simple quantum theories of gravity that we have, where we can just really do all this stuff most completely, are ensemble theories. So there just isn't that answer. Yeah, they're an average over unitary theories. So anything that's true for sort of all unitary theories will also be true for them, and you know, all those answers you can get. But anything that's like these calculations aren't telling you anything about the particular unitary that happens in the evaporation. It's just telling you that it's some unitary, or it's an average over unitaries or something.
And do you think that this is a technical limitation, or it's something? I mean, that
No, it's not like it's we don't understand enough about quantum gravity limitation.
So you need
like
to know about the microstates of the theory to be able to answer this question.
Yeah, I think, yeah, basically. Like it's, yeah, I think there's just, we shouldn't expect the effective field theory to know about that. Right? The sort of the paradox of, the reason the information paradox was so profound was that it, for all the world, it seemed like the effective field theory should be able to give you the right answer, but it seemed like it didn't. And so it was like, oh, somehow the sort of UV completion and the microstates and all that sort of stuff have to be showing up to get the answer to all here. But I think the lesson of the last year is that, no, actually, you know, general theory of effective field theory is right. These things that we should have been able to calculate with effective field theory, we can calculate with effective field theory, and we have, but we're still no closer to being able to answer the questions that you can't answer with effective field theory. Like, what's the theory of replica? What are the microstates?
Can I ask a question, please? Sorry, it's a bit late, but aren't you, in your entire discussion, aren't you implicitly assuming that there is a microscopic structure to the black hole, that there are microstates that we are used to in string theory? Actually, we know of examples.
So what I would not say we're assuming that. There's a recent review article that came out by you know, the East Coast Replica wormhole people, where they call it the like central dogma, that like the fact that there exists microstates, and you know that the Bekenstein-Hawkey entropy is calculating them and stuff, right? And you know, that dogma has inspired all these things like the page curve, but in these calculations, we're not assuming that dogma. We are just doing effective field theory calculations and getting answers that are consistent with that dogma, and therefore providing evidence that that dogma is true. But it's indirect evidence. It's not, you know, we're not like deriving that you know, we're not deriving anything directly about the microstates. We're showing that the consequences you should expect from microstates and unitarity and so on do indeed show up in the effective field theory.
Okay, thank you.
Any other questions?
When you said the central dogma, it reminded me of Francis Crick.
Yeah, exactly. They deliberately took it from there.
Oh, I see.
Yeah.
Thank you.
Question. So, you know, if you think of a string world sheet calculation of a string propagator, it has a sum over world sheets of various topologies. So you might say that there is no single two-dimensional world sheet quantum theory which describes this kind of a path integral. So it's necessarily an ensemble of quantum gravity theories, which...
Sorry, say that again. Why? This is the world sheet theory itself, thought of as a theory of quantum gravity.
Let us say I want to compute the sum over various topologies.
Yep.
Then I presume you would say that there is no single world sheet unitary quantum worldsheet theory, which describes this topologies. Is that the kind of idea for the wormhole?
Yeah, I probably would say that. I think the interpretation. I think you need to have some like interpretation of those worldsheets in a sort of third quantized way as like, you know, universes joining and splitting, right? But I think normally when we would do string theory, then
Yes, I was going to
I think that is.
There is a string field theory kind of understanding where you have eventually a unitary theory which gives rise to all these stuff, which looks like non-unitary, which looks like an ensemble of first quantized string theories. So
I'd want to distinguish between, you know, the sum over topologies on the worldsheet in string theory and the sum over topologies in something like, you know, two-dimensional theory of gravity like JT gravity. I mean, as a technical thing, they are basically the same, but as a interpretational thing, then they're very different, right? In the like topology counting parameter in the worldsheet theory is like the string coupling constant, right? In JT gravity, we're interpreting it as like exponential in like like e to the minus s naught. So yeah, it's the same technical stuff going on, but in one case we're wanting to think of this as like worldsheet scattering amplitudes within some space-time, and then maybe that space-time would also have topology changing things if we understood the full theory. And in the sort of simple, you know, JT gravity and stuff like that, then the two-dimensional theory itself is the space-time. And so the topology changes are not just like Feynman diagrams within the space-time, they are topology changes of the space-time itself. Yeah, I'm not sure if that answers your question, but
I get what you're saying. Okay, thank you.
Thanks.
Any other questions?
Hello. Yeah. So, Geoff, can I just get back to some question that I'd asked in the talk? But you know, like, and you had given me an answer, and let me just try to understand whether whether I got it right. So the statement was that, you know, like the correlators, they just thermalize, they just decay, they don't see these wormholes. So it seems to me that what you're saying is that there are kind of, you know, like 2-3 kind of observables that are objects, in the sense that there's some objects where if you compute, if you're thinking of some very complicated correlators, then from the get-go, you know, even before page time, all the saddle points contribute, you know, like almost equally. And then there are objects where, you know, like the Hawking saddle point dominates always, which is a second type. And then there are objects which actually show a page curve, where there's actually a transition in page time. So is this a good way to understand?
I think I would disagree with the claim that complicated enough. Well, I would say before the page time, you can't make complicated enough operators that they will see anything non-thermal. There's just not enough degrees of freedom. Any correlation function will see. See that it's thermal.
Even e to the power s point functions. I mean, I can.
Yeah, I mean, e to the s rad would not be big enough, I think, until the page time. Think of it as the density matrix, and you're looking at, like, if all the elements of the density matrix in the sort of normal in a standard basis are thermal up to e to the minus Bekenstein-Hawking entropy corrections, and the matrix itself is only e to the s radiation by e to the s radiation, then the matrix has to be close to thermal if we're before the page time, if s radiation is smaller than Bekenstein-Hawking entropy. It's only after that point that you have this loss of control over the very complicated correlation functions.
But I would imagine that if you somehow like get an e to the power s somewhere, then you start picking up the e to the power minus s corrections to the density matrix. But
yeah, I don't think you can. If s is the Bekenstein-Hawking entropy, I think there's just not enough degrees of freedom in the radiation for you to get an e to the s black hole.
Mm-hmm.
It's just a limit to how complicated correlation function can be.
So I just want to understand. So is this true even if you're, like, say, thinking about out of time ordered correlators or something? Or is this a statement about
if it's so if all your operators are acting on the outgoing modes, then I don't think out of time order stuff is going to be interesting, because there's no dynamics happening on the outgoing modes. If you're doing out of time order stuff that involves ingoing modes as well, then that's like a different question. Now you're not just looking at the Hawking radiation, you're looking at all sorts of stuff. Right? Is that clear?
But yeah, but the dynamics, but if you're thinking about out of time ordered correlators of the outgoing modes, since they're coupled to the ingoing modes,
I'm saying change the dynamics so that they aren't like or only consider the, like, if the Hawking radiation is getting reflected back in, then you're not getting evaporation and you're not getting, right, that's what's coupling them together. So consider the Hawking radiation that doesn't get reflected back in, which presumably is some if you're actually having an evaporating black hole.
So maybe one thing that's causing confusion is that if I understand correctly, you're describing the setup where you have some sense in which you've precisely separated off the Hawking radiation into a reservoir, so you can make that precise. And Loga might be talking about a slightly different.
Yeah,
I mean, if you have precisely separated off, then it's clear there's a page curve. I mean, Loga, you just think of a CFT coupled to a reservoir, and before the page time, you do whatever you like on the reservoir, and you just don't have the information about the the CFT state. Because
that I agree with. I think my question was for example, there is this statement that that Jan de Boer and collaborators worked out, which is that if you couple a string to a black brane, okay, and then if you look at the quark, the dual quark, then in some sense, if you look at the out of time ordered correlators of the quark, you see that it is also maximally chaotic. In some sense, it's a very simple system, okay. But since it's coupled to a plasma, which has complicated dynamics, the out of time ordered correlators of the simple Brownian particle picks up the maximal chaos of the environment. So there's a sense in which simple operators, because they're coupled, they can, out of time ordered correlators can pick up the scrambling information and so on and so forth. If you think of this maximal chaos as a kind of, I think.
I want to avoid a situation where it's I just think once you're talking about a situation where it's not clear there's not a clear separation between Hawking radiation and the stuff that's falling into the black hole, then I think it just gets a lot more complicated you have to be a lot more careful about what's encoded with what and stuff like that, right? Like if you're having degrees of freedom at different times that do not commute with each other, and you're talking about them both being in both being Hawking radiation, then it's not clear to me like what the entropy of that would even mean. It's not clear to me all sorts of things. Now I'm not saying you can't make stuff precise still, but yeah, it seems to me it's a lot more simple when you have a situation. If you just consider situations like flat space, or like where you extract it into a reservoir, or like a small black hole in ADS, where you have sort of, you know, this large region where the radiation is just free streaming and it's not getting reflected back in or anything, where you can just say, yeah, this is radiation. We sort of have it all at one time. And we can talk about how many degrees of freedom of radiation we're looking at and things like that. Yeah, I'm not saying there's not sensible things to say in more general situations, but it seems a lot more complicated to me.
Okay, thanks.
Any more questions? Yeah, it seems that there are no more questions. So many thanks, Geoff, once more, and thank you everyone for joining this seminar. So I wish you stay safe, stay healthy, and I also wish you a very nice time ahead. So bye bye for now.
Yep. Thanks.
Thank you.
Thanks,
Thank you. Thank you very much.